In this video, we are going to look at some important concepts in thermodynamics. Actually, this video is in two parts. I decided to split them in order not to make the video very long. So the first part, we are going to talk about the thermodynamic potentials. And in the second part, we're going to see how we can use these potentials to derive the Maxwell's relations. So first watch this one, then I will leave the link somewhere up here or in the video description so that you can continue to the next part. Okay, so the thermodynamic potentials actually are functions or quantities that give us important information about the state of any thermodynamic system. There are four of them actually. They include the internal energy, the Helmholtz free energy, the Gibbs energy, and the enthalpy. So we're going to look at each of them and derive the expressions. So the first one here is the internal energy. Internal energy U. Okay. So the internal energy of a system is simply the amount of energy contained in that system. And yeah, we can obtain this directly from the first law of thermodynamics. If you recall the first law of thermodynamics, it tells us that the heat change of a system is its change in internal energy plus the work done against external forces. So we can obtain delta U directly from here, the internal energy, as delta Q minus delta W. Okay, and delta Q, actually, we can get the expression of delta Q in terms of the entropy. It's just, so that's delta U equals, that's T ds. So T, let me say T delta S, since I'm using delta. So T delta S is the expression of delta Q. And then the work done is just the pressure times the change in volume. Okay, so this is the expression of the internal energy. So usually we can write it in differential form as du equals T ds minus P dV. So this is the expression of the internal energy, and it's the first thermodynamic potential, which gives us the internal, the energy content of any thermodynamic system. Okay. So the second thermodynamic potential here is the Helmholtz free energy. Helmholtz, I hope I'm writing that word, free energy, which is usually denoted by capital F. So the Helmholtz free energy is the energy available in the system to do work at constant temperature and volume. So it's given by F equals U minus Ts, and we can obtain the differential form of this by just differentiating this expression. So dF is equal to du minus, we differentiate this using the product rule, so that's T ds minus S dt. And then we can replace the expression of du by this. That's going to be T ds minus P dV minus T ds minus S dt. And if we simplify this, because this can cancel with this, so we are left with negative S dt minus P dV. Okay, so we can write the F as negative S dt minus P dV. And this is the expression of Helmholtz free energy, which reflects the energy that a system has for work, the energy available in a system to do work at constant temperature and volume. And then if we want the differential expression, then you can see that we have dF as a function of any temperature change dt and any volume change dV. So the variables really that come into play here are T and V. So we can say that F is just a function of T and V, okay, or dF if you prefer. All right, so let's move to the third thermodynamic quantity, thermodynamic potential. Okay. And so that's the Gibbs free energy. Usually denoted by the symbol G. Usually denoted by the symbol G, capital G. So Gibbs free energy here refers to the energy that a system has and that it can use to do non-mechanical work at constant temperature and volume. So by non-mechanical work, we mean here that the volume of the system does not change, so delta V is 0. And you recall that delta W, the work done, is P delta V. So if delta V is 0, it means that delta W is 0 as well. So the energy content of the system in such a situation is known as Gibbs free energy. So it's given by G equal U plus PV minus TS. Okay, and as we are going to see, this is actually just the fourth thermodynamic potential, which is known as the enthalpy, which reflects the total energy of a system. So U plus PV is the enthalpy. We are going to look at that in the next in a few minutes. So we can get the differential form of G. So dG, we need to differentiate all through this expression. So that's du plus P dV, okay, plus V dP. We differentiate using product rule, then minus TdS and minus SdT. Then here, what can we replace? We can replace delta du with the expression we got here above. So that would be T ds minus P dV, then plus P dV plus V dP minus TdS minus SdT. So you can notice that this term would cancel with this one. This term cancels with this one. So we are left with dG equals negative SdT and then P plus V dP. So let me put that in green. So this is the expression of this is the differential expression of Gibbs free energy. Okay, so what you can notice is that Gibbs free energy is actually the volume is constant, as you can see. So dG is a function of temperature and the pressure at constant volume. And this really reflects the fact that the system does no mechanical work. The temperature and pressure can change, no change in the volume. And this reflects it can do chemical work but no mechanical work. Hope that's clear. So let's move to the last quantity, which I already mentioned subtly. So that's the enthalpy, which has a symbol H. So the enthalpy refers to it refers to the total energy content of a system. Okay, and usually it is useful for systems or processes that occur at constant pressure. So H is just U, the internal energy, plus PV. So this is the total energy content of a system. Then if we want the differential form of H, dH, it's just going to be du plus P dV plus V dP. So we can simplify this. Again, we can replace du with that expression. So that's T ds minus P dV, then plus P dV, and plus V dP. So we can notice that this cancels with this, such that we are left with dH equals to T ds plus v dp. So that's the expression of the enthalpy. dH equals T ds plus V dP. All right. So what you can notice is that dH is a function of the entropy and the pressure. And here, the temperature is kept constant. Okay, so these are the 4 thermodynamic potentials that are used in thermodynamics. They are very important quantities because they really enable us to understand the energy content of a system and various forms of work that can be undergone. In the next part of this video, okay, I'm going to post the link somewhere here. We are going to see how to use these expressions, each of these potentials, to derive Maxwell's relations, which are very important quantities too, that simplify a lot of the calculations in thermodynamics. So see you in the next part.